Imagine a world where buildings stood for millennia. Not just a few hundred years, but 2,000. A world where harbors defied the relentless ocean, where monumental domes soared for centuries, unfazed by time, weather, or even earthquakes. This isn't science fiction. This was the reality of ancient Rome. Our modern concrete crumbles, cracks, and corrodes in mere decades, demanding constant repair and replacement. But the Pantheon, the Colosseum, and countless Roman harbors? They're still here. Why? What forgotten magic did the Romans possess that we, with all our advanced technology, still struggle to replicate? For centuries, engineers and historians scratched their heads. How could a civilization without reinforced steel or complex chemical labs create a building material so superior to our own? The answer lies not in magic, but in a brilliant, almost accidental, mastery of natural chemistry. The Romans didn't have Portland cement, the foundational ingredient of virtually all modern concrete, which requires immense energy to produce and releases significant carbon dioxide. Instead, they used a mixture of volcanic ash, lime, and seawater. Seems simple, right? But the genius was in how these seemingly basic components interacted. The key ingredient was Pozzolana, a naturally occurring volcanic ash found near Pozzolana, Italy. This specific ash possesses unique properties. When mixed with lime and seawater, something incredible happened. Modern concrete hardens as water evaporates, leaving behind a brittle, porous structure susceptible to cracks and rebar corrosion. Roman concrete, however, was different. When seawater met the volcanic ash and lime, a slow, ongoing chemical reaction began. This wasn't just a rapid drying process, it was a process of internal growth and transformation. Over time, new minerals, particularly a rare calcium aluminum silicate hydrate known as tobermarite-like crystals, began to form within the concrete itself. Think of it like this: modern concrete is inert once it cures. It's done. Its strength is fixed, and its vulnerabilities are set. Roman concrete was alive in a chemical sense. These crystals grew and expanded, actually reinforcing the material from within at a microscopic level. More astonishingly, they actively filled microcracks as they formed, effectively making the concrete self-healing. This self-repairing mechanism is why Roman structures submerged in corrosive seawater are often in better condition than their dry-land counterparts. The constant presence of water, especially seawater rich in reactive elements, didn't degrade it, it actually strengthened it over millennia. The Romans inadvertently created a concrete that thrives on the very elements that destroy our own. Consider the Roman harbors, some of the most enduring structures on Earth. Submerged for 2 millennia, battling powerful waves and salt corrosion, they remain largely intact. Our marine concrete installations typically last only 50 to 100 years before succumbing to the relentless assault of the ocean, costing billions in repairs and replacements. The Roman formula wasn't just stronger, it was fundamentally different. It embraced the environment, leveraging natural forces to become more robust over time, rather than deteriorating. This wasn't merely a construction material, it was a geological process in fast forward, creating a new, ultra-durable stone that literally gets stronger with age. This ancient technology wasn't just about longevity, it allowed for architectural feats previously unimaginable. The Pantheon's massive unreinforced concrete dome, still the largest of its kind at 142 feet in diameter, is a testament to this material's incredible compressive strength and light weight, achieved by using lighter aggregate in higher sections. Can you imagine designing a structure today, knowing it would stand for 2,000 years without significant maintenance? It's a paradigm shift in how we approach construction, sustainability, and legacy, forcing us to question our assumptions about progress. So, what is the ultimate secret? It's not just the Pozzolana, nor just the lime and seawater. It's the precise combination and the resulting ongoing chemical reactions that create a dynamic, self-healing material. Researchers have finally begun to unlock the atomic-level intricacies of this ancient recipe. They discovered that the Romans used hot mixing techniques, combining quicklime directly into the mix at high temperatures. This created superreactive lime clasts, small, porous chunks of lime within the concrete. These clasts, previously thought to be simply imperfect mixing, are now understood as critical. When cracks form, water penetrates these lime clasts, triggering a secondary reaction that produces calcium carbonate, effectively patching the cracks from the inside out. It's a truly self-healing system, not a static, inert one like modern concrete. This isn't just about replicating an old recipe, it's about fundamentally rethinking how we engineer materials. The truth revealed is that Roman concrete wasn't just strong, it was intelligent. Its internal chemistry allowed it to adapt, heal, and endure, making it arguably the most advanced construction material in history. And as we face a global concrete crisis, with crumbling infrastructure and massive carbon emissions, perhaps looking back at the ingenuity of the past is the only way to build a sustainable future.